What you're watching is the complete manufacturing journey of a forged crane hook from Pengsheng Forging, one of China's premier forging companies. And this process is far more involved than most people realize. It starts with raw steel billets being heated in a furnace to around 200 degrees Celsius. That's over 2,000 degrees Fahrenheit. At that temperature, steel becomes malleable, almost like thick clay. The billets are then transferred immediately to the forging press. The forging press slams down with thousands of tons of force, shaping the red-hot steel into a near-net hook form. Multiple die strikes are used to gradually form the hook's shape, ensuring the grain structure of the steel flows along the contour of the hook, not cut across it. That's critical for strength. After forging, the hook goes through a controlled heat treatment process, normalizing and quenching, to refine its grain structure and achieve the required mechanical properties like tensile strength and impact resistance. Then comes machining. CNC lathes and mills cut the mounting threads, bore the hook's inner diameter, and finish the load-bearing surfaces to tight dimensional tolerances. Next, the hook is sandblasted to remove all scale and oxidation, giving it that uniform matte finish you see here. Finally, it's ground and polished at critical wear points, then inspected visually, dimensionally, and with non-destructive testing methods like magnetic particle inspection. If you've ever been curious about what goes on inside a modern machine shop, the kind that supplies parts for the aerospace industry, automotive giants, or even your local industrial equipment dealer, today's clip is going to blow your mind. We're looking at a Haas CNC lathe, one of the most trusted and widely used turning machines in American manufacturing. Haas Automation, founded right here in the US back in 1983 in Oxnard, California, has become the largest machine tool builder in the Western world. And there's a reason shops of all sizes, from small job shops in the Midwest to precision aerospace facilities in California, rely on Haas machines day in and day out. They're built tough, they're reliable, and they're programmable with a level of precision that would have seemed like science fiction just a few decades ago. Now, what makes this clip really special is that the machinist isn't loading a pre-written program from a computer or a USB drive. He's manually entering G-code commands directly into the Haas control panel, line by line, right there at the machine. That's old-school skill-meeting, cutting-edge technology. G-code is the universal language of CNC machining. It tells the machine exactly where to move, how fast to spin, and how deep to cut, all in a series of precise numerical commands. Commands like G00 for rapid positioning, G01 for linear cutting, G96 for constant surface speed, and M03 to start the spindle. These are the building blocks of every part this machine produces. Watch as the operator first sets up the workpiece, a solid metal billet clamped securely in the chuck. Then, using the Haas control panel, that iconic gray interface with its color screen and full keyboard, he begins keying in the program. Each line of code is deliberate and precise. There's no room for error when you're working with tolerances measured in thousandths of an inch. Once the program is entered and verified, he hits cycle start, and that's where the magic happens. The spindle accelerates, the cutting tool engages the workpiece, and layer by layer, the raw metal is transformed into a perfectly dimensioned component. The lathe handles everything from facing and roughing passes to finish cuts with a surface quality smoother than glass. This is real American craftsmanship, the kind that built this country's manufacturing backbone. And even today, in the age of full automation, it's the skilled hands and sharp minds behind the machine that make all the difference. What you're watching right now is heavy-duty milling on a scale most people have never seen up close. This metal workpiece measures a full 1.2 by 2 meters. That's roughly 4 by 6.5 feet of solid metal sitting on a massive machining table. And the machine doing the work? That's a gantry-style CNC milling machine, the kind built specifically for large-format industrial components. The cutting tool you see there is a face mill loaded with carbide inserts. each insert engineered to withstand extreme heat and pressure. With each pass, the spindle removes layer after layer of metal with remarkable precision. We're talking about material removal rates that can exceed 50 cubic inches per minute on a roughing pass like this. What makes this kind of machining so impressive is the sheer rigidity required. The workpiece is clamped down with enormous force. The machine bed is built from cast iron or welded steel, sometimes weighing 50 to 100 tons, just to eliminate vibration. Because at this scale, even a tiny vibration means a flawed surface finish or a broken tool. This is the kind of work that goes into building molds for ship propellers, bases for turbine generators, and structural components for aerospace. Every pass brings this massive block one step closer to a precision part, and that's something truly worth stopping to appreciate. What happens to all that scrap metal, old car frames, discarded machinery, leftover industrial parts, after it reaches the end of the line? Well, in the right hands, that waste becomes something incredibly valuable. Today, we're going inside one of the most advanced metal recycling operations in the world. And trust me, this process is nothing short of remarkable. It all starts at the intake yard, where a 4-ton mobile vibratory handler, sometimes called a vibratory feeder or shakeout unit, takes in the raw scrap material. This machine uses precisely calibrated vibrations to break apart clumped or interlocked metal pieces, sort out fine particles, and feed the material steadily into the processing line. It handles up to 4 metric tons per cycle, ensuring a consistent and controlled flow of scrap into the smelting system. Next, the sorted scrap is charged into the heart of the operation, the TR 12-15-ton tilting rotary furnace. This is a beast of a machine. Fueled by an oxygen-enriched burner system, it reaches temperatures exceeding 400 degrees Fahrenheit, hot enough to melt virtually any aluminum or non-ferrous alloy scrap within 90 to 120 minutes. The rotating drum design ensures even heat distribution, maximizing melt efficiency and minimizing metal loss. The tilting mechanism allows precise, controlled pouring without manual handling, safer, cleaner, and far more efficient. From there, the molten metal is transferred to the 15-ton tilting shaft holding furnace, a specialized unit designed to maintain the liquid metal at a stable temperature while preparing it for casting. What makes this furnace truly impressive is its porous plug gas injection system. Inert gas, typically argon or nitrogen, is forced up through a porous ceramic plug at the furnace floor, bubbling gently through the molten bath. This process, called degassing, removes dissolved hydrogen and other impurities that could weaken the final product. The result is cleaner, denser, higher quality metal ready for casting. Now we enter the casting floor, and this is where things really get impressive. The facility runs 220 ingot mold casting machines, each equipped with an indirect water cooling system. Here's how that works. Rather than spraying water directly onto the hot metal molds, which can cause thermal shock and surface defects, water flows through a closed cooling jacket surrounding each mold. This indirect method controls the cooling rate precisely, reducing internal stress in the ingots and producing a uniform grain structure. The result? Ingots with superior mechanical properties and excellent surface finish. Once the ingots are cast and cooled, a robotic stacking line takes over. These industrial robots, equipped with specially designed cooling clamp grippers, handle the still warm ingots with incredible precision. The clamps are engineered to grip each ingot firmly without marking the surface, while simultaneously drawing heat away from the contact points to protect the robot's mechanisms. The robots stack the ingots into perfectly aligned bundles, ready for shipment. And throughout every step of this process, a comprehensive air pollution control system is working hard behind the scenes. Fume hoods, high-efficiency filtration units, and a continuous emissions monitoring system, or CEMS, track particulate matter, sulfur dioxide, and other pollutants in real time, 24 hours a day. This system ensures the facility meets, and in many cases exceeds, the strictest environmental standards. Today, we're going inside Hebei Longma Steel Pipe Manufacturing Co., Limited, one of China's leading LSAW pipe producers, to see exactly how it's done. LSAW stands for longitudinal submerged arc welding, and it's one of the most demanding and precise pipe manufacturing methods in the industry. These pipes are used in high-pressure applications where strength, dimensional accuracy, and weld integrity are absolutely critical. The process begins with large steel plates, thick slabs of high-grade carbon or alloy steel, precisely cut to length. These plates enter the forming line, where they go through a series of pressing and bending operations using heavy-duty JCO forming presses. The J, C, and O in JCO refer to the progressive shape the plate takes on as it's bent, first into a J, then into a C, and finally pressed into a full O, a round tubular shape. This multi-step cold forming process ensures the pipe maintains consistent roundness and wall thickness throughout its length. Next comes the critical welding stage. The preformed pipe shell is first tack welded along the seam to hold its shape, then moved to the internal submerged arc welding station, where the inside seam is welded first. A submerged arc process means the welding arc is completely buried under a layer of granular flux. This shields the weld from atmospheric contamination, produces an incredibly clean and strong weld, and virtually eliminates spatter. Then the pipe moves to the external SAW station for the outside pass. After welding, every pipe goes through a mechanical pipe expander, a hydraulic mandrel that stretches the pipe from the inside to its final precise diameter. This step relieves residual stress from the forming and welding processes and guarantees dimensional accuracy to within fractions of a millimeter. Then comes the most important step of all, non-destructive testing. Every single weld seam is inspected using ultrasonic testing and X-ray examination. These tests can detect the tiniest internal flaw, a microcrack, a void, a lamination, without ever cutting the pipe open. Only pipes that pass every inspection move forward. Final steps include hydrostatic pressure testing, end beveling, anti-corrosion coating, and dimensional verification before each pipe earns its quality certification and heads out to customers around the world.